Hi, I'm Jayden, a high school student, and today everyone will hopefully be learning about kernel task switching and an implementation by me at Rust. So the first thing we need to know is what really is task switching, right? So when you're using any operating system on most computers, right, you have a lot of tasks, or you can call these processes or apps, although apps is a bit more of a vague term, that need to run in parallel. So if you can see from the screenshot taken from my computer, this is HTOP, by the way. The equivalent of it would be Task Manager on Windows or Activity Monitor on Macs. There's a lot of tasks, and they're all running in parallel, right? So how do we actually run these tasks on a CPU? Well, the obvious solution at first would just be to put each task on a separate CPU core. So here in this diagram, we have core 1, we have task 1 on it, core 2 has a second task, core 3, core 4, so on and so forth. But what if there are more tasks than CPU cores available, right? So say we have a 5th task here, but we only have 4 cores. Then if we have more tasks than cores and we still want to run them at effectively the same time, we need to put multiple tasks on each core and then switch between them really rapidly to simulate them running at the same time. So the act of switching between 2 different tasks on a core is called task switching. And deciding what task to run and when to is called task scheduling. And these 2 things, task switching and task scheduling, together they form a multitasking system. Almost all modern operating systems are multitasking systems. So in this visual, there's only 5 tasks and 4 cores, but in reality, most modern operating systems are juggling much more than this, if you can remember from my screenshot. So today, we're mainly going to be going over a task switching implementation in Rust with a simple task scheduler. But a bit of a preamble here, right? So there are 2 main types of multitasking systems. So basically different like scheduling algorithms. In a cooperative system on the right here, each program decides when it wants to stop and give CPU time to another program. And then an outside scheduler decides what to run next. So async Rust code is a cooperative system. And at each .await, you basically let whatever async runtime you're using, such as Tokyo or async stud, decide what to run next. So in like the cooperative pseudocode example here, we spawn 2 tasks. Each of them will print task started, they'll wait 1 second, and then they will print task completed. So what really is happening here is that, say you spawn 1 task, it prints task started, and then at the .await on the sleep call, basically it's telling Tokyo runtime or the task scheduler that, okay, you can give the CPU to another task now. And then the other task begins, it prints task started, they both wait for a bit, and then they both print task completed. So that's a cooperative system. The opposite of this is a preemptive system. In a preemptive system, all tasks are fully controlled by an outside scheduler. So they can't choose when to yield and give time to other tasks. And this outside scheduler gives some amount of time to a task when it switches to next, until it switches to the next one. So for example, this time might be like a set amount, it might be like 10 milliseconds, or it can be a variable amount depending on how important the task is. Now, most operating system kernels use preemptive switching. And actually, Rust stud thread uses these native OS threads. So what's happening in this code on the left is that the kernel will rapidly switch between task 1 and task 2, along with other threads from other processes, and the kernel is fully responsible for that. So today we'll only be talking about a preemptive system, but I think the core switching logic can be used for both. Although if you are using Rust and want to make a cooperative kernel, you probably just want to use async and make your own runtime or use an existing embedded runtime. And now we're going to be going into a bit more technical stuff, a lot of x86, 64 specific stuff, and specifically. If you don't know what this is, just think anything with a modern Intel or AMD CPU. And some ground rules. So for what we're going to be showing, I'm going to make a few assumptions for the sake of complexity and just to keep this talk short. So the first thing is that I assume that we're on a single core system, which means that, the computer we're running on only has a single core. And then we're going to be using a very simple scheduler. We're basically just keeping a circular list of tasks and then just running them one by one with like a set amount of time given to each one. So these two things combined basically means that we don't need to worry too much about the scheduling algorithm. We don't need to, decide, what core will we put the task on and how to switch between all of these. And then lastly, since we're talking about a kernel, we're just not going to be going into user space where most actual programs in modern operating systems run. So if you don't know what user space is, just think of it as privilege levels, right? We're going to be staying at the kernel privilege level, which is the highest one, instead of going into, like lower privileges with user-controlled programs. So we're going to be staying at the level of the kernel. So before we can switch from task to task, we really need to know how, a task runs. I've been using it in somewhat of a vague term up until now. So let's, dive in to see what actually a task is. So all that a task is really that there's just instructions written in machine code somewhere in memory. And the CPU's job is to execute these instructions sequentially. And it knows where these instructions are because it has a pointer stored in a register. So if you don't know what a register is, it's basically small, really fast memory stored on each CPU core itself. So there's general purpose registers. They serve like no special meaning to the CPU, and programs usually use these to store variables or pass in function call arguments or do arithmetic. And there's also more special registers that have distinct meanings to the CPU, so special meanings to the CPU. And all of these registers, general purpose registers or special registers, all have three-letter names. So RIP, register instruction pointer, is the instruction pointer. And it's a special register because it has significant meaning to the CPU in that it is pointing to the next instruction that's going to be executed. And aside from registers, the second part that most programs have, or tasks that need to have, although it's not strictly required, is a stack. So the stack stores stuff such as larger data, think like a struct that is too large to be stored in a register. Most registers are 64 bits, by the way, and function call frames. So the fun thing about a stack is that there's two operations you can do on it. You can push from the stack, and then you can pop from the stack. So what that's really doing is that there is a pointer, RSP, which is register stack pointer, and it always points to the top of the stack, right? And when you push to the stack, you push a value to the top of the stack, and then the pointer gets actually decremented, but the pointer gets moved up. And then when you pop from the stack, the pointer gets moved down. So one small detail is that the stack actually doesn't grow topmost, it actually goes downward. So basically, when you're pushing to the stack, you're actually putting a location below where the current top, quote unquote, top of the stack is. And then the pointer is getting decremented, it's moving downwards. And then when you're popping from the stack, the pointer's moving up. So for all of this, there's commands in machine code and, the human readable equivalent assembly to, push and pop from the stack, move values around in registers, and so on and so forth. So here we have quick little example program to demonstrate all the things that I just talked about. So this program will move the value 42 to RAX, which is a general purpose register. It'll move the value 73 to RBX, which is also a general purpose register. And then it pushes the value stored in RAX to the stack. So you see that RSP right now is pointing to the top of the stack, and then RIP is always pointing to the next line of instructions that's going to be executed. And then we push the value of RBX to the stack, and then we pop those in opposite order. So as you can see, the values of both of them actually have been switched. So now that we know generally what a task kind of is and how it runs, we need to have a bunch of tasks and actually switch between them. And to do this, we need to be able to store the state of each task even when it's paused. So we have a PCB or a TCB process or task control block. And the two main things that it stores are, number one, the execution state of the task, and number two, the registers of the task when it's paused. The registers of the task, basically, as seen in the previous example, store all of the running state of the task. So if we just load them in, then we can expect the task to continue running. And then there's two less important things, which are the task type, which is very important for, I guess, user space tasks if you want to switch privileges, and you need to be able to differentiate if the task is kernel or, by the user. And the stack start, which I also keep a pointer to, because, that's a useful identification of, which task it actually is. We also need to have some sort of mechanism to trigger the task switch. So, the first thought might be to just put it in some background thread and let that thread periodically send a message. But, well, that requires an operating system implementation of tasks in the first place. Thankfully, each CPU core, as well as the system itself, most computers have this, they all have timers. And the good thing we can do is that we can program the CPU timer to periodically give a quote-unquote interrupt, which then we can attach a handler to, and then jump to code that we want to execute when the interrupt fires. So let's imagine that we have the small program that I just showed, right? So it's in the front of the task queue, it's running right now, and there's another task behind it with RBX set to 99 and a lot of the other registers. So say an interrupt happens right now, like when the task reaches the state of the slide. The first thing we do is we save all of the registers of the task, right? So here we only show 4 of them, but in reality, there's a lot more. We save all of the registers of the task into its control block. And then we put it to the back of the queue, and then we put the next task to the front of the queue. We load all of the registers of the next task, all of its general purpose registers and all of its special registers. So now you see that the stack pointer is pointing to the next task, stack, and then the instruction pointer is pointing to the next task's instructions. And then now basically this task is free to run and continue where it left off when we first paused it. So this is somewhat of a more high-level overview. So now let's get into how we actually pull the registers into the task control block and how we actually load all of these registers from the task control block when we're loading the next task into the actual respective registers themselves. So now let's get into some code and learn along the way. But right before that, a quick note on calling conventions. Calling conventions are basically things that specify how a function is going to be called and, the details on how the compiler will handle it. For example, they specify where function parameters are going to be passed in and where results are going to be returned. So they can specify registers or on the stack or whatever. So all we need to know is that on most x86 systems, the following rules apply for C functions. So the first 6 integer arguments are usually passed in RDI, RSI, RDX, blah, 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 blah. Additionals are passed on the stack. And then the results are going to be returned in RAX and RDX. So you don't need to memorize this for now, but it will become important later. And then also knowing what calling convention a function is, compilers will usually add extra code to the beginning and end of a function and compile the code inside the function accordingly to meet these calling conventions. So, well, here it is. Here's the entire scheduling code. First thing you can see is just this big function that's just a huge block of assembly. And then we have this smaller function down here. We'll get to that later. Let's just focus on the big function for now. Actually, let's focus on line 5, the unsafe naked attribute. So naked just means that the function is going to be pure assembly, right? And the compiler won't add anything to meet any external calling conventions. This also has the effect of a naked function just not being able to take in arguments or run Rust code or return anything, because that would involve meeting a calling convention and adding extra instructions to the function. This naked attribute actually was only on nightly Rust before I gave this talk, but I think it's recently being stable. So now onto the function signature on line 6. First we see unsafe because we need it for the naked asm attribute, which goes with unsafe naked. And then we have extern x86 interrupt. So normally what this thing would do, normally it's used to, the extern keyword usually is used to specify calling conventions, and it's not very different here. It would usually meet the x86 interrupt calling convention and add some code to the beginning of the function and the end of the function to make handling the interrupt easier. And it abstracts away some details, but this actually doesn't do anything right now because of the naked attribute. The reason I include this is because, well, if you're going to be making a scheduling system, you're probably going to be using the x86-64 crate, which is, in my knowledge, the only one which abstracts away, handling, well, interrupt handlers and a lot of x86 specific stuff. And what that crate expects is a function with this exact signature. So you probably want to add this onto your scheduling function. Sorry, that was a bit of a rant there. But now let's go on to the code. So from line 8 to line 22, we see that it pushes all of the registers of the current task onto the stack. So remember, this piece of code is running right when an interrupt fires in the middle of a task running, right? So all of the registers that are on the stack at the beginning of this function are the ones of the current task. So what we're going to do is that we're going to push all of those onto the stack. And then on line 23 and 24, you see that it calls schedule inner with the first argument being the stack pointer. You might look at this and say, well, how are we actually calling it with an argument, right? Line 24, we only say call schedule inner. But if you remember from the C calling convention, the first integer argument is always going to be passed through RDI. So on line 23, we move the stack pointer onto RDI, and then we call schedule inner. So as long as schedule inner is a function that we tell the compiler that it's going to meet the C calling convention, what we're effectively doing is calling schedule inner with the stack pointer being the first argument. So if you look down here, schedule inner, we put extern C here to tell the compiler that it's going to match the C calling convention. We'll get into what this schedule inner actually does in detail later. But what we need to know for now is that schedule inner takes in the stack pointer, right? And then it modifies everything on the stack, because everything on the stack is right now the registers of the current task. It's going to modify everything. It's going to first save those registers into a task control block, and then it's going to modify all of those on the stack to be the ones of the next task in the queue. So now, after that, all of the registers on the stack are of the next task. And then from line 26 to 29, we send end of interrupt to the CPU, which basically means that we are handling the interrupt. And then we pop all of the registers of the next task into their actual respective registers off of the stack from line 31 to 45. So just from this, basically we've switched tasks. We have loaded the next task's registers into the actual registers. Thereby, we've loaded the entire state of the next task, and it can just continue to run. But what you might notice is that we're not pushing or popping the stack or instruction pointers, nor any other special registers that might have significance to the CPU, right? So how is it updating them so that the new task actually runs and then the stack is correct and then the instruction is correct, right? For that, we need to know what happens during an interrupt, actually. So at the start of when any interrupt is triggered, it pushes all of these registers onto the stack in order. So first SS, RSP, RFlag, CS, RIP, and then an optional error code. So let's go over what all of these actually mean. The stack segment is actually not very important right now. We don't need to worry about this too much, but you might want to know that in older systems, this was very crucial for their different memory representation, but this is mostly legacy now. And then the stack pointers push next. This is obviously important because we need to know where the current task stack is. R flags, this is a special register that's used for arithmetic state by the CPU. There's some CPU flags on there. It's pretty important, but all you need to know is that it's just part of the state of the task. The code segment, like the stack segment, it's mostly legacy, but one thing is that it's still important because it stores the privilege level, although we don't use that right now, so you can ignore that as well. And then lastly, it pushes the instruction pointer from before the interrupt. So it's basically like the return address of the interrupt once it's handled. So it's where the function's left off, which is also important because we need to store that. And then some interrupts push an error code, but not the one we're working with, which is the timer interrupt. So that's not very important. So let's go back into the main schedule function. So before the function has even ran, the CPU has already pushed a bunch of registers onto the stack, including the stack pointer and the instruction pointer, the two arguably most important ones. Then we do all our stuff. We push all the current task registers, call schedule init to swap those with the registers of the next task, and then we pop the new registers. And then you might want to note that the schedule init function also swaps the stack and instruction pointer, as well as everything that the interrupt has already pushed onto the stack before this handler, with that of the next task. So then we pop all of the general purpose registers, and on line 42, this is important. What IRAQ basically does is the exact opposite of what the CPU does at the beginning of an interrupt. It pops all of those stack off of the stack in reverse order. So basically we have the new task's instruction pointer and stack pointer and R flags and everything else loaded into their actual registers. And then, at the end of this, we've effectively completely switched tasks. We've saved all of the registers of the previous task, and then we've also loaded all the registers of the next task. So I know that probably wasn't entirely clear, so let's do a quick visualization and also go into what schedule init does line by line a bit. So right now, before anything has actually, anything in the handler has executed is when the interrupt has just fired, right? So you see on the stack, we already have SSRSP, RFlag, CS, RIP, all of the registers that the interrupt that the CPU pushes right when an interrupt fires. Let's go down. Then we push all of the general purpose registers onto the stack, right? So these are the registers of the task that was just interrupted. And then we call the schedule init function with the stack pointer as the first argument. So let's look at the schedule inner function. You can see that it takes in a pointer to the struct called task registers. So remember, we pass in the stack pointer to this when we call schedule inner. But we haven't named this thing stack pointer. We actually named it current task context. So why is this so? Let's look at the definition of the task registers struct. The first thing you probably want to notice here is that it is of repr C, which on line 3 is circled or boxed. What this basically means that the compiler is going to store this or represent this in memory the exact way that C is going to do it. And by chance, C actually does it where each field of this struct is going to be stored exactly in the order that is defined. So if you were to create an instance of the struct and put it in memory, R15 would be first, and then R14, and then R13, and then R12. So all of the fields are sequentially stored in the order that they are defined. So we see that task registers, we might notice that task registers is exactly the format of the current state of the stack right now, after we push all the general purpose registers, and also after the CPU has pushed all of the registers at the beginning of the interrupts. So it looks reversed because if you remember, the pointer is actually down at the lowest point of the stack, so right after R15. So in essence, by passing in the stack pointer to schedule inner, we're perfectly giving it a window, a structured window, to all of the current tasks registers to save and replace with the next task tasks. Practically, if you have a pointer to the top of the stack, and then you cast it to a pointer of task registers, we can access the value where each register was just pushed onto the stack just by accessing the field of this struct. And by doing this, we are able to call into an inner function with high-level Rust instead of writing all the inner scheduling logic in assembly. So back to this. On line 3, first we get the list of tasks. So that's the task queue. And then we copy all of the current task context onto the current task control block on line 12. So you see that we're doing current task.regs equals the current task context. So where current task comes from is on line 6, which basically gets the frontmost task because that's the task that's actually running. And then we're saving all of the registers of the task, which we passed in as a mutable raw pointer to task registers onto the actual task control block. And then we get the next task. Oh wait, first we push it to the back of the queue, of course, unless it has already terminated. And then we run the next task, which is now at the front of the queue. And how do we run it? So basically we just copy all of the registers from that task control block into the actual registers themselves by doing on line 21 unsafe deref of current task context equals task.registers. And then we also set the next task state to running, which is obvious. So after we return from the function schedule inner, the stack is full of the next task's registers. So it effectively makes up all of the state of the next task, so on the stack right. And then we pop all of the general purpose registers of the new task out. And then we call iretq, which makes the CPU pop off all of the registers that I pushed at the beginning of the interrupt. And now we've officially switched the tasks. Thanks for listening, everyone. And the code is pinned on my GitHub if you ever want to check it out. Thank you.